Okay, so here we are. We're back. Now, my apologies. I accidentally compiled the other video. It's been a common occurrence with me. I've been so absent-minded lately, and it's okay. It's okay. So, here we have the squeeze theorem. And the squeeze theorem here says that if we can find an inequality to bound our middle function g of x, we want to bound it from below and from above. And if we find that as we bound this function, as your x value approaches a, if your function from below and your function from above both evaluate to the exact same limit, then that must mean that your middle function, g of x, must also evaluate to the exact same limit as x is approaching a. So that's kind of really neat to consider there. So to illustrate this, I'm going to use an example here. This example is that we need to find the limits as x is approaching 0 for x to the fourth multiplied by sine of 1 over x. Now, again, you can try direct substitution, but again, direct substitution isn't going to give you anything beneficial here. Simply because when you're looking at sine of 1 divided by 0, well, anything 1 divided by 0 is undefined, which means sine of an undefined value, yeah, I'm sorry, that doesn't work. So we have an issue there. So we need to bypass it. And the thing about this type of limit is that we cannot bypass it using our typical algebraic manipulations or piecewise functions that we used back in part A, part B, and part C in the previous example. However, we do have something beneficial. That beneficial item here is the squeeze theorem. And we want to make sure we can use that squeeze theorem to our benefit. So where I start here is I want to start with a function that's going to bound, or that's going to give me bounds. The nice part about this is that I see a sine function. So here I'm going to say recall, and actually all of my recalls are in orange, so I'll make that orange. I'm going to say recall that sine of x is bounded by 1, or the absolute value of sine of x is bounded by 1. This comes from trig, saying that we can have sine being bounded between -1 and 1. And this is where you can look at the amplitudes for sine. If you remember the amplitudes for sine, well, the amplitude is 1 because the maximum value is 1 or -1 measured from the positive x-axis, which means you're only attaining 1 or -1 as its maximum amount. Maximum or minimum amount. So this is exactly where we start. So we start there where we say observe that sine of x is bounded between -1 and 1. Now, anytime that we change the amplitude, we change the bounds, naturally. However, if we change the period, we don't change the amplitudes whatsoever. So if I change the period to, let's, instead of being x, say call it 1 over x, well then at this point in time, my amplitudes still stay exactly the same. And the reason I'm doing this is because now what I'm in the business of is making sure that what I started with, this bounding option, that I try to match the initial expression that was given to me. Well, I have the sine of 1 over x. All I need is x to the fourth. So what am I going to do now? Well, I'm going to multiply every single component of this inequality, by x to the fourth. So every single component is being multiplied by x to the fourth. So now everything is being bounded, or at least this particular expression is being bounded from below and from above. I want to now take the limit of each individual piece. So let's look at the limit as x is approaching 0 for negative x to the power of 4. Limit as x is approaching 0 for x to the 4th times sine of 1 over x. And then the same thing here, limit as x is approaching 0 for x to the 4th. Okay, now the middle piece here, the middle part of this inequality, that's what we're trying to solve for. We don't know. However, look at the bounds from below and from above. From below, the left side bound, that's limit as x is approaching 0 for negative x to the 4th. Well, that limit evaluates to just be 0. What about the limit from above? Yeah, the limit from above does the same thing. Now look at what we've done here. We've sandwiched this limit that we're trying to find, that we have no idea how to evaluate. We've now sandwiched this limit between two values. Coincidentally, it's the same value of 0. Which means by our work, what must happen? Well, by the squeeze theorem, we managed to squeeze this function to arrive at the conclusion that this limit evaluates to just be 0. Let's go ahead and let's look at this on GeoGebra and see what we kind of did here. Okay, so follow me along. Okay, here we are on my friend GeoGebra. Okay, so we started off with sine of x. All right, there we go. There's sine of x. That's what we started with. Oh, look at that. It's orange too. Nice. I like that. Okay, so we started off with sine of x, and then we said, okay, well, yeah, sine of x, it's bounded by its amplitude. Look at that. So the y values are being bounded here between -1 and 1. Awesome. Then I said, you know what? I'm going to take that value for p of x, or that sine of x. So I'm going to take sine of x, and I'm going to change its amplitude, or not its amplitude, its period. So I'm going to go with 1 divided by x. So that's 1 divided by x instead. And that turns into this function here. Again, notice I was changing the period here, and therefore it gets us still what looks like a sine curve, except it bunches up a lot in the middle. And then what we said here is that, okay, now we want to multiply by a quantity of x to the 4th. So I'm going to introduce a quantity of x to the 4th here. Okay, so x to the power of 4. There we are. So here's my function x to the 4th. Now I want to multiply my function that I came up with, that sine of 1 over x, by x to the 4th. So I'm going to take my functions here, and I'm just going to multiply them together times r to the 4th, or x to the 4th, which is just r. Oops, wrong one. Which is q. There we go. So my function here of x to the 4th times sine of 1 over x looks like this. Let's look at what x to the 4th looks like. There we are. So here's x to the 4th. Let's change the color on this. Let's make it blue, and let's make it a little bit bigger. There we are. Here's the function in question. All right, so I'm going to make this function red. Make it a little bit thicker. There we are. So there's my function in question in red. X to the 4th is here in blue. Now I'm also going to continue with a different function because we bounded it from below with negative x to the 4th, and that's this function here. So I want you to then start observing this, that our function, this red function, is bounded above by this blue function, and that blue function was x to the 4th. Look at that. Now as x is approaching 0, x to the 4th remains up top. As x is approaching 0, this green function, negative x to the 4th, remains below. Therefore, as we're traveling along the function in question, as x is approaching 0, it's collapsing the boundaries that we bounded this by down to 0. Therefore, we don't need to know what the calculation for the limit is. We just need to know that we found two bounds that work as x is approaching 0, and we found it. And this is how we can conclude that the limit as x is approaching 0 for the quantity of x squared x to the fourth times sine of 1 over x is equal to 0. And that's by using the squeeze theorem. On your exam, you will get a squeeze theorem question, and I will need to see this type of similar work. So you must be able to produce something similar to this. And that is it for this section. I hope you all enjoyed it. Again, my apologies for breaking this section into 2 videos, but I hope it's not too detrimental to your studying. So I will see you all here for the next one, where we will be learning about the precise definition of a limit. Till next time.